Hi class, today we're going to be discussing isotopes and atomic mass. This is chapter 4.5. I've tried to give some good examples. This is a chapter, at least according to the isotopes, students tend to have a problem with. So I'm going to try to break this down as best as possible. Let's start out with atomic symbol. Atomic symbol, it can vary in different ways, but we're going to, sometimes the atomic symbol can have just the protons, the mass number, or both. We're going to carry atomic symbol as meaning having the mass number and the proton number with the element. So when you look at this, you'll see that it's magnesium. It has a mass number of 24. The mass will always be more than the proton number. And then you can either subtract these, because as the numbers get bigger, they get a little harder to understand to get to neutrons. But this is the proton number. This is the mass number. For atomic symbol, that's a term you should definitely know. Isotopes. Isotopes are the same element. They contain the same number of protons. That does not change. But they have a different mass number. And what that mass number means that they have more neutrons in with that different isotope. Some of these periodic elements do not have isotopes, and some do. We're going to point out a few that do. And we need to know how to calculate them. So let's first focus on the atomic symbol here before we start jumping into isotopes. Atomic symbol, symbol of element, mass number, atomic number. They will always have a different number with them. You may not know it until you start looking at the periodic table that you're dealing with an isotope and not the regular element that we tend to use. So let's focus on writing atomic symbols. So here we have oxygen. We have phosphorus, and we have zinc. So when you look at this, you should know how to break down the information that we just covered in 4.4 regarding protons, neutrons, and electrons, and mass number. So if we look at these, we have this atomic symbol, mass number, and protons. So these are neutral, so that means the atomic number is the same as the proton number. And then we have the mass number, we can fill that in. And then we have number of protons. And how do we determine neutrons? We subtract the mass number from the atomic number, and that gives us the number of neutrons. Same here. With phosphorus, we have 15 as the atomic number, so that's the number of protons. And the mass number is 31, so we subtract the mass number from the number of protons, and that's going to give us the number of neutrons. Here it's 16. And zinc, we have an atomic number of 30, a mass number of 65, and the number of protons is 30. And we're going to subtract the mass number from the number of protons, and it's going to give us neutrons of 35. Okay, so here is an example of an isotope. An isotope is, again, same element, contains a same number of protons, so none of these have different number of protons. Protons is that fingerprint for that element. So in this class, that will never change. So if we're dealing with magnesium, it has 12 protons, but it has different mass number. So if you see here that the atomic symbol for 24, so you see this is the mass, this is what's on the periodic table. This one has a mass of 24 and an atomic number of 12, and 78.70% makes up. So if we were to search for magnesium, we would find that there is an abundance of 78.70% of a magnesium with a mass of 20. And over here, we find an isotope that has a mass of 25, which means that this one does not have the same number of neutrons that this one does. This one has 12, and this one has 13. So here, this percentage is 10.13. There's a huge difference between these numbers. So if we were to search, we would find that out of the magnesium we find, 10% of it is at this mass of 25. And we would find that 11% of it, approximately, has a mass of 26, which means these neutrons are also different than this one and this one. Now, so this is the one that is the most abundant. But when we take the average of these, in consideration to the percent, it's a weighted mass, and this is the average of all three isotopes that you see on the periodic table. You can tell that most of it is at 24. Not at 25, and not at 26. But the 0.31 takes into account these, and it's based on the percentage. The bigger the percentage, that's what's going to control what the mass number is on the periodic table. We've got more examples. So here is a breakdown. Again, the mass on periodic table is 24.31. You see that it's all magnesium. The number of protons do not change here, 12, 12, and 12. The number of electrons do not change, 12, 12, and 12. The only thing that changes, actually there's two things. The mass number, which is an indication that you're dealing with an isotope, and the number of neutrons. So for magnesium 24, which has 12 protons, it has 12 neutrons and a mass of 24. 23.99, and it makes up of most of the isotopes found. It's 78%, almost 80%. Magnesium 25, and it'll either be written like this or like this. That's how you know you're dealing with an isotope. Either one of these two rows, this is how it's going to be dealt with. If you ever see just Mg by itself, then we're not taking into consideration that that is a normal let's say magnesium atom, and we would take whatever is listed on the periodic table. In order for it to be an isotope, it's going to be like this or labeled like this. If it's just Mg, then look at the periodic table for the information you need. Here's 25. So protons are 12, mass is 25, neutrons are 13. It has a mass of 24.99 at 10% of it. And 26, so we have number of protons 12, mass number is 26, number of neutrons is 14, a mass of 25.98. And when we find this, we find that 11% makes up mass of 26. Then we take the average with the percent and the mass, and that's how we have the mass that we have on the periodic table for this element. So carbon also has isotopes. It has carbon 12, carbon 13, and carbon 14. And that's how you would speak of these: magnesium 24, magnesium 25, magnesium 26. So this is asking for a breakdown just like what we did here. So if you were to look at a periodic table, which I'm just going to jump ahead on this, carbon, all of them have the same proton number, does not change. All have the same electron numbers, does not change. The difference is the mass, which you see here. This is also atomic symbol, where this is an indication that it is an isotope. It may not have the proton number underneath, but this is also written like this. So this is 14 minus 6 gives us 8 neutrons. 13 minus 6, the protons, gives us 7. And 12 minus 6, the protons, gives us 6 neutrons. So you don't handle them any differently. You just take the information you're given and you go forward with it the way you have been. All right, so let's talk about writing atomic symbols. We're now going to write atomic symbols with the mass and the proton number. So let's take a look at what this first one is. We have 8 protons. So if we have, I'm jumping ahead. Yes, we are. So I picked, of course, a periodic table that didn't have a mass on it, but we don't need it. We want to take it from the information we have here. So the first one has 8 protons, 8 electrons. So we don't really need to worry about the electrons right now. These are neutral atoms. So we have 8 protons and 8 neutrons. If we add these together, that gives us a mass of 16 and an 8. So we know that this is oxygen. We should have written oxygen, and then next to it, a 16 above. The mass is always more than the proton number, and then 8 underneath. The next one, we have 17 protons, so we have chlorine, and we have 20 neutrons, so that's 37. We are going to write it in the same way that we did with oxygen, and 37 above, 17 below, and then the symbol. Now we have 47 protons, so let's see, we have 47 in. 47 is silver, and we have 60 neutrons. So we're going to have 107 as the mass, 47 as the proton number, and then the chemical symbol. Which pairs of below are isotopes of the same element? So the key thing here is we want to know if it's the same element, it has to have the same protons. If it does not have the same protons, it is not to the same element. You are dealing with 2 different elements on the periodic table. So this is really easy. Your eyes should know that the bottom line is the proton number. So this matches. This is isotopes of each other. One has a mass of 12, one has a mass of 14, but the proton number for both is 6. So this has the same atomic number, but different masses. Now let's take care of question 2. In which of these pairs and which of the pairs below do both atoms have 8 neutrons? Now, this question's not asking for same element. So we are going to be dealing with 2 different elements. We are interested in 2 elements that have 8 neutrons. So let's take a look at the top one. This is the mass number. 15 minus 8 is 7. 15 minus 7 is 8. So this one's out. This one is 6 neutrons. This one is 8 neutrons. So it's got to be this one. 15 minus 7 is 8. 16 minus 8 is 8. So it would be C. Both these elements at the bottom, these isotopes, have 8 neutrons. Okay, so I brought this up briefly. We're going to focus more on it. Atomic mass. So the atomic mass that's on the periodic table, if it has isotopes, all the isotopes are considered into the atomic mass you see on the periodic table. It is a weighted average. And what the weighted average means is the amount of the percent that makes up has the more of the say on the atomic mass that we read. So chlorine here has 35 at 75%. And chlorine, this isotope, chlorine 37, has 24%. So as you can see, this mass is more towards 35 than it is towards 37. The 0.45 is giving into consideration to the 37 by raising the amount above 35, because this percentage isn't a very small amount. It's about a quarter, and this is 3/4. So this weighted average, we average these out based on the percentage, and then we add them together, and that is the percentage that we see on the atomic on the periodic table. Sometimes we might need more information. Let me take that back. I don't want to get too far ahead. So ignore this last sentence I just said. All right, so I'm going to show you how to do this. And this is where students have a hard time. This is not that difficult. This is, again, going back to algebra. A lot of students that have problems that they believe are chemistry problems are actually not chemistry problems. The chemistry part is not the issue. It's the algebra. It's reading, understanding how to translate what's being asked of you, and then putting it into an algebraic form to solve it. So it's not most of the time, it's never the chemistry, it's the algebra. Okay, so we need to determine the average weighted mass, the mass that we see on the periodic table. If we were given isotopes and a percentage of them, we are going to use the experimental percent abundance of each isotope, and then we're going to multiply the percent abundance by the atomic mass of that isotope, and then we're going to add them all together. So I put this form together. This is not the form you would see. It's not the original formula. The original formula has a sigma sign here and a sigma sign here, and it gets really complicated if you don't understand what sigma means. So I just left it in a way that makes it a little easier to understand. You have a percent abundance, you divide that by 100, because we do not want it in percent form. We want it in decimal form. Then with that, a percent abundance with the isotope, you multiply them. Same here, and then you add those together, and that, depending on how many, if you have 4 of these, you do 4. If you have 3, you do 3, you do 2, you do 2, and that will give you your average weighted mass. Follow sig fig rules. So here is an example with my formula. A large sample of naturally occurring chlorine atoms consists of 75.76% of 35 isotope chlorine 35 and 24.24% of chlorine 17. Oh, I think I messed that up. That should be 37. I apologize. Here should be 37 and not 17. You can verify it right here. I accidentally put the proton number. The chlorine 35 isotope mass is 34.97. And the 37 chlorine, see, I fixed it here. Isotope is 36.97. We want the weighted average. Now, I just showed you what the weighted average is, but let's make sure that we know how to do this. So the first thing you do, take the mass of the chlorine for isotope 35, which is right here. And then you take the percent abundance and you divide it by 100. So this here has to be divided by 100. You cannot use percent form. Then there should be parentheses here. So this one is done, and then this one's in parentheses, and you do the same to this one. And then you add these amounts together, and that gives us the atomic mass. So if we look here, we have the 36.97, and we multiply it by the percent that's been divided by 100 to get the decimal form. Same thing here, and this gives us a 35.45 AMU, which is the weighted average mass of both the isotopes. This one here is this amount, this one here is this amount, and then we added them together. This takes a little time to understand, but it really is not as difficult as I think books make it to be. Figure out the formula, and if you can figure out the formula, you can do these problems very easily. And you can even do harder ones, because sometimes they'll give you everything but maybe this value and you have to solve for it. But that's where the x is going to come in, that you'll have to isolate x and solve for it. I might ask about the percent. You'll have to solve for x there. So this is why it's good that you understand how to start moving variables around, or at least remember, because you should come in with a certain amount of math, even if you're rusty on it. As long as you're working on it, that's all that matters. And you can move things around to solve for problems that are not just always set like this, but if I move it around and ask for different things in this, you can solve for it. So here is a list of atomic masses, and the percentage that has the highest percentage usually is the one that defines the amount that you see on the periodic table. For instance, you have lithium-6 and lithium-7. The atomic mass weighted average here, this is what you see on the periodic table. You can obviously tell that this is closer to 7 than this is 6. So without even knowing the percent abundance, you know that this one dominates because the mass is more towards this one. Carbon has an atomic mass of 12.01. So what you see on the periodic table matches this isotope. So this means that this isotope makes up almost everything, and the percentages here have to be so little that they make only a 0.1 impact on here. And the same thing for if you look at oxygen. Oxygen is 16, 17, and 18. It is at 16. So these have to be trace percentages, really, really, really tiny percentages. They don't even make an impact. And then some don't have any isotopes at all. And so fluorine does not, and then you can see sulfur does, and so forth. So if you look at it and you look at the atomic mass, that should instantly tell you which isotope has the most say in what the mass is, or the average mass is, that you'll see on the periodic table. So lithium consists of two naturally occurring isotopes, lithium-6 and lithium-7. I put this here so nobody had to look for a periodic table. We want to know which one's the most prevalent one. Covered it on the previous page. The mass is 6.94, so it tells you that the most prevalent one is lithium-7 because the atomic mass is so close to 7. All right, so that's what I pretty much did here. And let's do one more problem. Gallium is an element found in lasers used in compact disc players, CD players. Here is a sample. We have 60% of gallium-69 and 39.90% of gallium-71. We want to know what the weighted atomic mass is. So we're going to plug this in the way that we had. You take the mass of the first one, take the mass of the second one, take this one out of percentage, divide it by 100, take this one out of percentage, divide it by 100. Then you multiply this one together, multiply this one together, add them together, and it will give you the weighted average. And 69.72 means that this one has a higher percentage. It's more going to match this mass of 69 over the 71. But it's not close to 70 as much, but it's closer to 69. So this is a far higher percentage abundance of it. Okay, and that is it. Thank you.